Good afternoon. My name is Milena, and we are SkyRats. SkyRats is an extension group created in 2017 by students of Escola Politécnica da Universidade de São Paulo, whose main objective is to develop, design, and research autonomous drones. We are currently supported and sponsored by Universidade de São Paulo, EP-USP, Grêmio Politécnico, CIT-USP, and Fundo Patrimonial Amigos da Poli. Our Cobruf team is composed of 20 people, representing 3 different universities and various education levels. We were instantly driven to this year's challenge because we believe it is our duty as developers to always use curiosity as a driving force towards innovation and new discoveries, such as the exploration of space. The methodology used by the team is model-based design, which is a mathematical and visual form of addressing issues in designing embedded systems, such as signal processing, communication systems, and complex control. Besides MBD, we counted on brainstorming as a tool for generating new ideas and solutions. So today, we are going to showcase our final aerial robot project for Mars and the research and methodology on which it was based.
Drone design. We proposed an innovative design focusing on 3 important topics: modularity, agility, and sustainability. For the modularity, the design allowed the drone to transit between a tricopter, a quadcopter, and a hexacopter by disassembling parts and recombining them. Different combinations of sensors are possible too. For the agility, the drone fittings are simple and efficient, which turn the assembly and disassembly a quick and agile task. For the sustainability, once the drone is modular, only parts of the drone need to be produced instead of an entire new drone, saving resources and turning the process more sustainable. The form of the drone. To determine the best shape, tests with different forms such as cube, a sphere, an ellipse, and a star were made using a software. The red dots represent particles with higher velocity, and the green dots represent particles with less velocity. In the results, we can see that the Earth located in front of the ellipse is smaller than on the other tests. So we concluded that the best form was the ellipse, and we decided to study the influence of the variation of the constants A and B on the ellipse equation. These results were important on the parameterization of the drone. Parameterization of the shape. For the parameterization, we used the triangular form as a reference and defined some constants. All the forms of the drone are contained inside the circumference of radius r, as in the image. Then we could obtain the equations for the different forms by making an orthogonal projection of one side face of each form. For the triangular shape, we obtain these equations. For the square shape, we have these equations. And for the hexagonal shape, we have a special condition where the limits of the orthogonal projection on the x-axis of one side face is the diameter of the circumference, which gives the extension of the ellipse in this case. Finally, some restrictions that must be considered. The maximum extension of EX is the length of the hexagonal edge, and the limit of EY is the bigger ellipse. Thank you.
Good afternoon. My name is Lucas, and I'm responsible for embedded system architecture. In this part, we are going to talk about the hardware concept and software architecture. Note that in Figure 1, or Figure 7, shows the hardware system architecture. There are 2 main layers. On low-level layer, there is a flight controller unit. On high-level layer, there is the high-level computer. Okay. The flight controller unit is responsible to control directly the flight tasks. In order to solve this, it runs the firmware. By definition, it's the low-level software embedded system and the real-time operational system. To accomplish the design requirements, we choose the fixed fault flight controller unit because it has the ARM Cortex architecture processor. Okay. and it's responsible to control directly the flight tests. On this 32-bit ARM Cortex architecture processor, it's possible to run the PX4 autopilot software. On table 1, we can take a look at the Pixhawk 4 specifications. Note that there are a rich hardware interface. It means we can connect a lot of sensors and actuators to flight controller unit. For example, there is the I2C interface. This protocol architecture allows us to connect all the design sensors in the same bus. Okay. Now we are going to talk about the high-level computer. The high-level computer is responsible to do the complex tasks. For example, the high-level state machine, an artificial intelligence application. We choose the NVIDIA Jetson TX2 because of its powerful hardware. We can note in table 2 the specifications of this board. It has basically 80 gigabytes of RAM memory, and its ARM processor is equivalent Intel Core i7 processor. There is too much power processor. So here we can take a look at this board. We use this Jetson to develop softwares in our drone. We can take a look at more specifics now. Now we are going to talk about the software architecture. Such as the hardware, we divided our software architecture in two main layers, the low-level layer and high-level layers. On low level, it runs the firmware PX4 autopilot, and it runs the real-time operating system NUX. On high level, it runs the Linux distribution Debian Strat 90.5. Okay. To illustrate this, we can take a look at this prototype. The SkyRats team developed this drone during this year. So we can take a look at this board. This is the Pixhawk, the flight controller unit. Then we can take a look at this board. This is the high-level computer. In this case of this drone, we cannot use this board because of this size and this shape. So we opted to use this board. We can take a look at this component. This is the electronic speed controller, and it's responsible to control the electrical current flowing to the motor. This is the electronic speed controller. Then we can take a look at this motor, and this is a brushless motor responsible to propel the drone. So I forgot to mention this in hardware architecture. So let's go to talk about software architecture now. The firmware PX4 is responsible to run the flight state machine. It's the flight step. This part is responsible to acquire data from inertial measurement units, barometers, gyroscope, and estimating parameters like position and drone velocity. From this information, the PX4 firmware is determining the flight mode, and then it describes the flight mode's state machine. The PX4 firmware runs based on Mavlink messages protocol, and it's a very important information. Okay. Sorry, it's the wrong slide. Okay. Now we are going to talk about the high-level layer. To develop the high-level applications, we use the robot operating system. It's a robotic framework that allows develop robots in high level in a scheme of messages publishers and messages subscribers. Inside ROS, there is a Mavros. It's a very important library responsible to do the conversion from ROS write level messages to Mavlink protocol. Thus, it's possible to do the connection between the high level and low level layers. Remembering the high level layer is running in this hardware, this board, as you can see. And the low level layer of software is running at this hardware, the Pixhawk. Just remember. And furthermore, in these layers, there are the artificial intelligence applications. For example, in order to identify persons, it runs a multi-layer perceptrons neural network. And this hardware is powerful enough to run this application. Okay. Now, finally, we can take a look at the simulation. The gazebo is an ambient associated to robotic operating system. The simulator we use in order to simulate our applications developed on ROS. So, for example, in this case, we developed an algorithm that the drone describes a square trajectory. As you can see, the first position, the second position, the third position, and the fourth position. And we can use this simulator in order to validate our algorithms design. Thank you very much.
Hi, my name is Kelvin, and I'm the responsible for the development of the subsystems system health analysis. In order to talk about this topic, first of all, we need to describe subsystems architecture displacement to support that feature. That part of the whole drone project is vital to know about the operability of the necessary components to take emissions tests properly accomplished. So it is necessary to design and prototype monitoring capabilities which are able to determine the operation level of these subsystems. Therefore, some faults may harm the mission accomplishment. We need to identify these faults before the worst, the mission failure. In this way, our team designed two principal sensors to get mechanical and power system diagnostics using the tachometer to verify the engine's operability compared to default data provided by an internal database, and the ammeter, what is used similarly the tachometer to inspect drone's electrical system. Finally, we must verify faults what necessary are not provided by the own subsystem failure, the consecutive fault. So, in order to fulfill this gap, we designed a consecutive fault verifier. Here we can see a model example done in MATLAB simulating software, where we have two decision models designed to show to the operator or to the artificial intelligence in drone how to proceed with a fault, what is consecutive. Okay. Other data useful to take a diagnosis about the system health analysis is the temperature of each subsystem. Very important to know possible system overload. The first element that we choose to use is the electrical resistant thermometers to analyze the drone's indoor temperature, and the second is the state temperature gauge designed to pick up data and about the external components which suffer the influence of the Mars atmosphere. Concluding, here we can see tachometer data specifications like the voltage dry contact, the size, the source, and the outputs, and a model that we use to do the cost planning. Okay, here we have the equations that describe this kind of system, where R is the resistance, ρ is the density of the air in force, and finally A is the area that we can, the drone's area, temperature, and the alpha coefficient that we determine to establish the correct relation. Okay, concluding this talk, we have the atmospheric sensing. Inside the project, this point was a great challenge to the team because many technologies required to support these features were only implemented in Mars probes. Therefore, we decided to search a little bit more about previous missions sent to Mars, and a great guidance to develop the subsystem was the Mars Pathfinder lander. Considering their definitions, we had designed the atmospheric air temperature measurement system as a series of 3 thermocouples installed in different points of drone's fuselage in order to get redundancy data to merge its results to create traceable information. Okay, to measure the atmospheric pressure, we decided to use the pitot system as the measurement of the speed of the airflow displacement. Finally, we have the measurement of an important, extremely important part of the drone, the air and ionizing radiation. In our project, we have chosen to use electrical detectors. Thank you.
Good afternoon, my name is Denis Sopanta, and I'm going to talk about the remote data exploration and data stream. The communication system is based on 2 types of data transmission, one for long range and telemetry, and one for short range, swarm work, and a good amount of data. The first one is a 915 megahertz with a capability of a 1 kilometer communication without spending a lot of energy. This system is responsible for the communication between central and the drones, making possible in emergency cases the central send commands to the drones. The second one is a 2.4 gigahertz with protocols TCP/IP and this TCP/IP. At this point, the drones are working one nearby other with an edge hoc controlled by their artificial intelligence. The TCP/IP in this case is used to don't create a mistake in orders between them and avoid crashes. Therefore, the system creates a small web communication for swarm work. This web will have one gateway, a drone responsible to link the swarm to the base. So, thank you.
Hi, my name is Fernando, and I will talk about how the SkyRats team find methane gas in Mars. Okay. To do that, we divide our strategy in 3 parts and 2 aspects, using chemistry and geography knowledge to determine regions with the highest probability to find it. The 3 steps are, look at the figure. 1. Recognize ancient oceans regions to shorten sedimentary basins and determine regions most likely to encounter methane. 2. Using a spectroscope, the drone will identify if the specific regions contain methane gas. And 3. The last step would be darting the soil and collecting sample of the soil to confirm the existence of methane in the site. But this biome is the scope of the remote sensing. So this step that is part of the process will not be performed by the drone. This is our method. Now, I will comment with some specific aspect of it. Cooperation between topographic images and maps. By comparing the topographic analysis of images obtained by the drone's camera to cartographic maps obtained by Mars recognized orbiter, the drone will be able to identify with reliable precision ancient ocean location on planet Mars. Okay. The spectroscope. A spectroscope is an equipment that uses electromagnetic waves to excite materials so that the radiation returned by them can be analyzed. This analysis is possible because each chemical element can each chemical element, when excited, emits radiation that, through a spectral analysis, can indicate the existence of the desired chemical element. And is the atmosphere on Mars is thinner than an Earth atmosphere? The UV radiation on Mars is more intense, so the regions most likely to encounter methane gas are those that are least exposed to UV radiation. To find these regions, CSP studies are used by analyzing the images obtained by the drone's camera, which will be processed considering the subbands on the light in order to obtain the specific information on relief. Thank you.
Hi, my name is Natalia, and I represent the Drones Features Building. As one of the requests for our drone was the capacity of building, we thought that the best way to do so would be attaching a robotic arm under the drone, which its precision and resistance. In the picture, you can see the prototype of the arm developed by us, with 4 links, 3 joints, and one caught in the hammer. We intend to know the Cartesian precisions. You just need to apply those 2 equations in function on the angle variation and the length of the arm. For catching the intended object, you apply those 2 other equations, being x and y of the coordinates of the objects. Thinking about where to attach the arm on the drone, it would be better on the center of the gravity. So take this side as being Cx, the center of mass, is Cx square root of 3 divided by 3, considering a triangular shape. For Mars habitats, we found out that the ideal shape would be a circle dome, which would be made by the triangles. Therefore, to build that, the drone will be used. The cloud from the arm to put in the triangles on exactly place, and to have this complete form. In the picture, it's possible to see how the building will look like. On our hypothetical mission, we thought about the establishment of an autonomous colony with the installation of a workstation and thermonuclear mini planes. Phase 1 is the shipping of 2 models containing the drones and required materials, the modification of the region using previous data from the MRO, and science, physical, and chemical analysis of the chosen location. Phase 2 is the construction of the workstation completely built by the drones containing the models. Finally, Phase 3 is the arrival of the first human team to start the thermonuclear mini planes and to make final adjustments that the drones are capable to do. Thank
you. We are going to talk about the astrobio sensor. This kind of sensor has so many technical difficulties, and we are supposed to get solutions to this problem. As the astrobio sensor is a great technology challenge, we get adapted some existence solutions to adequate to the Cobruf objectives. So, the sensor needs more, and the analysis techniques combination can be a reachable solution. Here are introduced 3 complementary procedures. 1, KCM, quartz crystal microbalance analysis technique that allows the identification of organic cluster of molecules, only passed in carbon verification. 2, EIS, electrochemical impedance and spectroscopy, that allows the sensor to detect deeper properties from the substrate from a default value. SPR, surface plasma resonance, that improves the sensibility level of the measurements. So, with of these 3 techniques, we are supposed to attend the requirements to build an astrobio sensor that, as I talked about before, is a huge technical challenge. Thank you.
Good afternoon. My name is Kyle, and I'm going to talk a little bit about water detection in Mars by remote sensing. So, we start facing this problem by analyzing water's interesting and peculiar characteristics. And after that, we can get to know the most common methods and technologies to detect those characteristics. Starting with the water's spectral signature. As mentioned before by our friend Fernando, the water spectral signature is the main tool utilized in the field of spectroscopy to detect substances. As shown in the graph, the water presents a relative low reflectance in quite a broad radiation band, which is visible in infrared band, basically, on this graph, compared to the other substances, such as soil. Although this graphs only the behavior of poor water when interacting with radiation. I mean, in practice, such a spectral signature is highly sensitive to impurities, not allowing us to predict water presence accurately based on its pure spectral signature, such as in this graph. Although we don't tend to use the pure spectral signature to detect substances. That's inaccurate and require precise machinery. We commonly use the spectroscopic indexes, which consists in a series of operations. Let's say you have two images from different hyperspectral bands. You perform operations between the pixels of those images, and therefore you can usually detect the substance that you want, basically. And that's made by analyzing the spectral signature from samples of the desired substance, as well for the undesired ones. And that's commonly done to notice from the sample considerable difference between their signatures and subtract images on those two bands, and then we normalize it, dividing it by the sum, in such a way that it only assumes positive values when you're looking for the right substance, the substance that you're looking for. Therefore, in Mars, we will need to get reference samples of the soil and generate a normalized difference index from the critical signature points, such as this one. Apart from that, water has another quite peculiar feature, which is its specific heat. This one is considerably high in comparison to other substances in the surface of Mars. Therefore, it's possible that we map with a turbo camera the difference in the surface temperature between two instants of time, and as the spectral indexes, subtract those images. That will give us the lowest specific heat part in the surface. So we can invert it to get a high specific heat substance, such as water. That's a good indicative of water in Mars, which, along with the spectral analysis, gives us a great indicative for the presence of water.
My name is Fabio, and I speak about the magical essence. Mars is a planet that has altered atmosphere characters to the human life, and its emergent situations. The red planet's conditions may promote the made missions on Mars. In order to support appropriate medical assistance, it was designed a rescue model that can be attached to the drone external supports. Its specs are distributed in the table 5. Education equipment AB established and true stable imaging connection to the base, where a health professional available to operate the drone's health features. Is external important to get an efficient medical assistance during the role mission as necessary. Therefore, a turbo chambers model was designed to support that kind of filter. The first chamber is an infrared collector, and the other is a night vision sensor. The final image is a result of the combining the best two images, which gives a great situation conditions. Vital to support suitable assistance protocol the operator. A possible standards for rescue procedure developed for this competition can be broadly exemplified by this machine state diagram. Automatically by identifying a digital signal, such as an alert inserted by the Cobruf Nauta for even reading of the biomedical signal created by his set. A drone examination is sent to rescue, where for carry the rescue model and one for the communication model. Upon arrival the rescue site, the professional at the base can take control to identify and coordinate rescue levers suitable for rescue. Upon completing these levers, again automatically, these drones return with clothing to the base. Thank you.
So our future work is mainly to study different sensors to accomplish the best results and the best price. Besides, we have the idea to make our frame and make tests on the air tunnel here at the University of São Paulo, and to make the aerodynamics test so we can study the best shape in Mars. Besides this, we think and study other sensors, more cheap, and anything else. So thank you guys for hearing us. We are open to the questions and answers right now. Okay.
Hi guys, thank you for your presentation. It was a really good one. Congratulations. And I have a few questions. First, what was the most difficult topic you faced during the project? I think you are muted.
Was the sorry
Okay.
because it's very hard to listen you because the audio is low. So
Okay, did you got the question?
Sorry?
Did you hear the question?
Yeah.
We heard it.
We heard
Okay,
it.
okay.
So we think the most difficult part in this project was to design the telemetry system, because our team is composed by first year and second year students. So we don't have the basis of the technical and the theory basis of electromagnetism to understand a lot of equations and methods to design these antennas and to understand how they work.
I got it. But you did a really good job. Apart from Mars, where do you believe are other great opportunities for drones on solar system exploration?
Sorry, could you repeat, please?
Okay. Okay. Apart from Mars, where do you believe are other great opportunities for drones on solar system exploration? Which other planets you think we could be using drones for exploration?
Okay.
With our equipment, we believe that best opportunity to explore the solar system is Europa and Titan moons. And the drone that we designed is technically capable to do this exploration.
Okay, and one of the main challenges, okay, I'll repeat it. One of the main challenges on Mars robotics is dealing with Mars dust. What would be the effect of Mars dust in your drone design and operation?
We think that the greatest challenge on dust on Mars, because dust on Mars is the engine's function, because these kind of engines are so sensible and dust can destroy some components than what is the most important in the drone. If you don't have the engines acting properly, we don't have anymore.
I have a compliment. We have the problem of the raising the drag. The drag will be raised with the dust in the atmosphere.
Okay, I understand. So to finish our presentation, do you want to say a few words before we finished?
Yes. 1 minute, please.
Huh? In the name of SkyRats, we thank you guys, the organization of Cobruf DRONES, and all the spectators. And come here, guys. We are the team of drones of Politécnica School on University of São Paulo, and are proud of our project in Cobruf DRONES. So thank you for hearing us. Goodbye.
Goodbye. Thank you.
Thank you.